Hello, in this recording, we're going to talk about mean value theorem. And first of all, we're going to, we have the statement of the theorem, and then we're going to talk about the proof. So let's move down row theorem. And mean value theorem has two premises, okay? So first of all, of course, f is a function. Okay, that satisfy the hypotheses, satisfies, okay, to try to make it short. And the two conditions of mean value theorem actually are exactly the same as the first two conditions for row theorem, okay? So for simplicity, I would just copy and paste here. So that way, it make it easier for us to know how many conditions there are, right? It's just the first two conditions without the third one. Okay. So the premises does not include the third one, so we don't need the third one. And then under these two conditions, okay, the conclusion is that there exists a number C, okay? And C is inside the interval such that the derivative of the function at C is equal to f of b minus f of a divided by b minus a. And what is that? And oftentimes we might be using the equivalence of this statement by multiplying both sides by b minus a. Okay, of course, we provide b is not the same as a. If we multiply both sides, so the other form that is often used is the derivative of f of c, okay, equals to that. Okay, so I'm just showing you how we get there. We multiply b minus a on both sides. We multiply that on both sides. As a result, on this side, b minus a and b minus a reduced. And we are left with f of b minus f of a. Okay, so let's first illustrate what this means. Okay, let's first illustrate what this means. Now, what is f of b minus f of a divided by b minus a, right? So I'm going to use this picture to illustrate. Okay, hold on. So I'm going to bring this picture. This is from the textbook. And we're just going to illustrate to you what it means. The first picture, this is the first picture. Okay, so there's a point A, there's a point B. There's a point A, there's a point B. Okay, and the curve from A to B, okay, the curve from f of A, well, from this point A, capital A to capital B, or capital B to capital A, doesn't matter. There's no sense of direction. And that's the curve. And the function is continuously and differentiably, made. Okay, so this is point A, this is f of A. Okay, the point, horizontal measurement, vertical measurement, b, f of b. So f of b minus f of a divided by b minus a, this is actually the slope of the blue line. Okay, so let me write it down. slope of the blue line is the rise over run. Okay, so f of b minus f of a divided by b minus a. So this is the slope of the point from capital A to B and that straight line. Okay, so the derivative of a point in C is between A and B, is the same as the slope of the blue line. Then that means since the derivative of a function at C is the tangent line, the slope of tangent line of the pink one. So the pink one and the blue line, they have the same slope. That means they're parallel. Okay, so this is the one case. And there is another case. Another case, it could be, of course, there could be even more cases, but the same idea. Okay, the same idea. So another case could be something like this. Okay, there are more than one C's between a lowercase a and lowercase b. And so the blue line, which is the secant line connecting the endpoints, and these two pink lines are parallel to the blue. And at C1, the derivative at C1, the derivative of the function at C1, which is the slope of this pink line, and the derivative of the function at C2, which is the slope of the P2 tangent line, they're the same. So all three are parallel. Okay, and this theorem guarantees there's one. If there's a one, then there could be two, even more. Okay, so that's the meaning of the mean value theorem. The mean value theorem. Okay, so let's look at the proof. Let's look at the proof. Okay, I feel the proof is a very interesting one because this proof is done by applying row theorem, and in the process, a special function is constructed. So I would like you guys to see how this special function is constructed. Okay, very interesting proof. All right, proof. Proof of the theorem. Okay, so first of all, suppose we just take this one. We just take this simpler case, right? Now, since we know, actually, we're not going to use this picture. We're not going to use the picture. I'm going to use the other picture. Okay, I'm going to use the other picture. This is also from the textbook. Okay, so let's give credit where it is due. Okay, so we have a function, which is, we want to see the construction of this new function, right? So the construction of this new function, first of all, we know that connecting capital A and capital Q, these 2 points, we have a secant line, right? So the blue line, so we call it blue line. This blue line, okay, this blue line is a slope, right? So the slope of the blue line is, okay, f of b rise over run, rise, this is the rise, overrun b minus a. This is the slope. And the equation of the blue line is, we can use one of the points, right? We can use point A or point B. We use point A, right? So the equation of this blue line is going to be y minus f of a, point slope formula, right? Point slope formula equal to the slope, which is the slope multiply x minus a, right? And of course, the slope is this piece. That is the slope of the blue line. So the equation, okay, that is the equation of the blue line. If we add f of a on both sides, we will get fy equals to f of a plus, you know, the rest of the parts. So this is the line equation of the blue line. The line equation of the blue line, okay? And next, we construct a function we call h. We construct a function we call h of x. H of x is constructed by taking the given function f of x minus the line equation. And what is the line equation? The blue line, okay? So the black curve is the function f of x, right? And point by point, we take every point, okay? We take every point. Let me draw a vertical line, okay? We take point by point, right? So this point is drawn here. You can see there's a part of this is, you know, take this point x, right? Take this point x. At this point x, f of x is this high, right? This is f of x. And the blue line is this much. So when we subtract f of x minus the blue, and we're left with h of x. So h of x is the difference between f of x and the blue line. I hope that makes sense. Okay, this picture is done so well, so I'm using it and credit to the textbook. Okay. Now you can see h of x is going to be the function that look like this algebraically. So f of x, we keep the f of x. Okay, subtracting y, and this whole thing is y. Okay, so we're going to put it in the bracket. We subtract that. If I open the bracket, right? So h of x would be equal to, if we open the bracket, is going to be minus f of a and minus the second part. Okay, so this is h of x. So now let's look at h of x. Okay, h of x, because f of x is continuous on the closed interval and differentiable on the open interval. Okay, f of a is a constant, and this is a constant, and x minus a is continuous and differentiable everywhere. So the h of x is continuous on the closed interval. Okay, so let's write it down. So this h of x, okay, we're basically checking the conditions. Okay, so first, h of x is continuous. Okay, it is continuous. So h of x is continuous on the closed interval. Okay, because f is continuous And we have a bunch of constant, and this x minus a is continuous, right? So according to the properties that we learned before about continuous function, and this is a continuous, h of x is also differentiable. Why it is differentiable? Because f of x is differentiable, and x minus a is differentiable. All the others are constants, right? And thirdly, the third condition, we're going to see if h of a, okay, so what is h of a? So in the function h, we're going to replace x by a. So x replaced by a, so that will be equals to all of these x's in this expression, x will be replaced by a. So x replaced by a. This piece is a minus a, that's 0. 0 times anything is 0. And f of a minus f of a is 0. So h of a is 0. Let's look at h of b, right? So we plug in b, h of b, f of b, and this is b, right? And what does that equal to? B minus a and b minus a, that makes 1 reduced, right? So we will get f of a minus f of b. So this piece is 1 reduced, right? So then we don't have to leave it here. So this piece, f of a minus f of b minus f of a minus f of b, and that is 0 again. So the third condition, i.e., h of a is equals to h of b. So all three conditions of row theorem are satisfied, right? All three conditions are satisfied for row theorem as when h is considered. So the conclusion for h will be applicable, okay? Then you say by row theorem, okay, there exists, okay? So the whole conclusion would be there exists C in AB such that the derivative of H at C is 0, right? So for such a C, what is the derivative of H? So what's the derivative of H? I'm going to take a derivative of H. Okay, so derivative of H, we take a derivative, so that takes derivative, and this piece takes derivative, that's going to be 0, right? And this is a constant, right? And we take a derivative of x minus a. The derivative of x minus a is 1 by chain rule, right? So in the end, the derivative of h is equals to, what does it equal to? It equals to that, right? The derivative of h, right? This is derivative of h. So let me rewrite it. The derivative of h equals to the derivative of f minus this constant. And for when c is substituted, right? Because at derivative of h at c is 0. So when we put c in the equation, right? So when this is replaced by c, the derivative of the function at c is 0, right? So h, the derivative of h at c is 0, but the derivative of h at c is also this piece, so this is true. If this is true, then what is it? And of course, we add f of b minus f of a divided by b minus a on both sides. So that is that, i.e. So that is the conclusion of mean value theorem. Okay, you can see the proof is very interesting. I would say it's very skillful proof. And that's the proof of mean value theorem. Okay, so now let's talk about how we apply mean value theorem. We're going to take a question from our homework. Okay, we're going to take a question from our homework, which is going to be from homework. Okay, let's take this one. Okay, take one of the questions. I would take number 12, which we did in classroom. So now this time we did it, we were going to do it again. The first example we're going to cover is the homework number 4 under that and number 12. So verify that the function satisfies the hypotheses of the mean value theorem on the given interval. Then find all number, okay, it could be plural, C, that satisfies the conclusion of mean value theorem. Okay, it's very similar to the examples that we did for row theorem, right? Verify, check every condition. But here, mean value theorem, there are only 2 conditions. Okay, so I'm going to copy and paste this condition, and we're going to just, for our convenience, we just check the conditions. And the function in our consideration is f of x equals to x raised to the power 3 minus 3x plus 2. The interval in consideration is -2, 2. Okay, so what we do is that, well, this is a polynomial. A polynomial is continuous everywhere, and certainly it is continuous on the given interval. And a polynomial is differentiable everywhere, as we learned in the previous chapters. So both conditions are satisfied. So we're going to mention that f of x is continuous on, and the interval is going to be from -2 to +2. And the other one is going to be the open interval. Okay. And then the mean value theorem conditions or premises are satisfied. And then you say, then there exists a C, right? So we're going to copy the conclusion, and C belongs to this interval, but this interval should be substituted by the interval we are looking at, such that, and this is true. This is true. And of course, we're going to have to put the actual function we have. From here, from the differentiable part, we could actually take the derivative right here. Okay, we can take the derivative right here. And the derivative of the function is going to be 3 times x squared. And this is going to be 3. And the derivative 2 is 0. Right? And we also need f of a, f of b, right? So we might just do it at this place. Okay, so f of -2 right? We need to, that's f of a. F of negative 2a is negative 2, so we're going to plug in this number. And when we plug in this number, be sure we insert parentheses as needed. Okay, so multiply negative 2 and evaluate it. That's a 0. And what is f of 2? Right, so we're going to substitute x by 2 in the function. So this way, f of b, f of a, they're all found. So this is 2, this is 2. Make sure you get the number properly expressed. All the numbers we need are, are found, right? So f of b now is f of 2, f of a here is negative 2, and b is 2, a is negative 2, right? And furthermore, if we substitute c in the derivative, right? We substitute c in the derivative. So we have a c here. So this is going to be 3 times c squared. So that would be the derivative of c that equals to the right-hand side. So we're going to put the numbers in place. Let's put the number in place. So f of 2 is 4. F of negative 2 is 0. And 2 minus negative 2 is a 4. So the right-hand side is really just 1. So we're solving for c. We're solving for c from this equation. Okay, we can remove that. This is nice and cleaner. So we're solving for c. And what do we get? What do we get? We're gonna add 3 on both sides. Okay, so we have 3c squared. This is a purely algebraic. 4, and we divide both sides by 3, right? So c squared is equals to 4 over 3. 4 over 3. And we take square root on both sides. Okay, we take square root on both sides. And what do we get on the right-hand side? Well, the square root of 4 is 2. 2 divided by square root of 3. If we rationalize it, right, by multiplying root 3 over root 3, and we are getting 2 times root 3 divided by 3. Okay, so on the left-hand side, we have the absolute value of c, which equals to 2 times square root of 3 divided by 3. And then to solve this, absolute value equation, we naturally get c equals to plus or minus that 2 times root 3 divided by 3. Okay, we got 2 c's. We got 2 c's. Then to draw the conclusion, to finish this question up, we need to say, wait a second, are these 2 numbers inside the interval? And apparently both numbers are inside the interval. Okay, so then we can answer the question, say, all the numbers satisfy the conclusion of mean value theorem. Okay, all the numbers. Thus, all the numbers satisfy the conclusion of the mean value theorem are these 2. There. And we're done. And we're done. Okay. So this is how we find the how we apply the mean value theorem. Okay. If you have any questions, please send them my way. And thank you for watching.